Hi, my name is URI Hyung. I'm going to show you my recent work about modeling the golden nanoparticles. That is a collaboration between experimental lab and a commission lab. So the golden nanoparticle systems are interesting because they give you precise tools of measuring the interactions between protein and the lipids. And our work is trying to build models of golden nanoparticles from scratch so that we can have physical understanding of interactions between protein and lipids at the interface. Specifically, we provide computation models so that you can have autonomous detail about what's interacting with which part. So, for example, people have done protein like alpha-synuclein interacting with the membrane lipids on top of a golden nanoparticle, and this will provide information about the secondary structures of the protein according to different curvatures of the golden nanoparticle, and we will be able to model different sizes according to experimental size and provide a better understanding of the interface interactions like this. This is just preliminary work, and this will be developed further as a tool for the nanobio nodes, which will be provided free of charge for scientists at large. That's it. Thank you.
Hi, I'm Yu Hangwan. I'm a visiting scientist. I'm from Professor Brian Cunningham School, and this is our work. So basically, in this work, we're trying to build a compact spectrometer system that can potentially be integrated into a smartphone for different types of biosensing assays based on spectrally resolved measurements of liquid phase samples. So here we build up a benchtop experiment with the linear variable filters combined with the CMOS camera, which is similar to the ones used in the smartphones. And with the linear variable filter, we are able to use them to take the place of the large diffraction gratings, so that we can compact the size of the commercially available spectrometers. So we did some fluorescence emission test and also the absorption measurement to test the performance of how this compact spectrometer work with the very common biosensing demonstrations. So for the fluorescence emission, we tested the spectrum of the different types of quantum dot emissions, and also we did the quantitative measurements. And for the absorption measurement, we test the different bands of the different food color dye, and then we did the quantitative measurements. And for the reapplication, we tried to test the water quality. We measured the different. We measured the free chlorine in tap water in Havana City, and you can see from the results that with the comparison of a commercially available spectrometer, our compact system, have very good and similar results, which agrees well with the commercially available spectrometers, which shows that this type of spectral analysis platform is suitable for this kind of measurements we are demonstrating here, and which has the system is simple, compact, and kind of easy to use. And in the future, it has the potential to be integrated into a smartphone, into a mobile devices like smartphones.
Okay.
Hello, my name is Mr. Garcia. I'm from Victor's Group Lab. My project is bio-inspired multispectral imager for image-guided surgery. The idea is that in cancer imaging, the main way to cure cancer is still to resect the cancer. The problem with that is the surgeon or the physician is going to assess that visually. So if the cancer is covered by healthy tissue, we're going to have a false negative, and the cancer is going to be resected. However, if the cancer tissue is on the surface, then the physician will see it and will resect it. The problem is that a lot of the times you have cancer tissue that is covered or surrounded by healthy tissue, and the surgeon will not see it. One solution to this problem is to do fluorescence imaging. The idea behind fluorescence imaging is that you inject a dye into the patient, and that dye is bioengineered to bound to cancer molecules. This dye fluoresces on a particular wavelength, and you use an excitation light source to excite the dye and see it with some kind of imaging system. Current state-of-the-art uses imaging systems use ICG, a dye called ICG, which fluoresces on the NIR. But current state-of-the-art technology uses two cameras, one for your NIR channel and one for your visible channel. So it is not possible for the physician to see in real time where the tumor is and resect based on the near-infrared information. What we have designed in our lab is multispectral pixelated filters based on the morpho butterfly vision. So these filters are inspired of the morpho butterfly, where the morpho butterfly uses tapetal filters. We're using the same idea by stacking different dielectrics of different thickness to tune the wavelength that we want to pass or reject into a pixelated filter. Unlike regular color cameras, where you have a Bayer pattern with two greens, one blue, and one red filter, we're using a similar idea, but instead of having two greens, we're replacing one of the green positions for an NIR filter. So you end up with 4 different spectrums. One of the photodiodes on your regular camera is going to be sensitive to the blue spectrum. Another one is going to be sensitive to the green spectrum. Another one to the red, and another one to the NIR. So we are integrating this into a single imaging sensor, meaning that the NIR channel and the visible channel are going to be perfectly co-registered, giving you sub-pixel accuracy. We're integrating this with Google reality, virtual reality goggles, where the physician is able to see the color image and the NIR image overlap on top of each other. Here we have some of the mice experiments that we have done. Here you see the color image of the mouse, and here in highlighted in red is the locations of the tumor. We are able to overlap these two images because it comes from the same sensor into a single image where the physician can see where the tumor is. We did some clinical studies to resect some cancer from a patient, and we were able to successfully resect the whole tumor using the fluorescence imaging technology.